All right, so in this video, we're basically going to show what happens when you heat a solid. And we're going to draw what's called a heating curve, or sometimes called a cooling curve. And it seems like a pretty obvious question at first. If you heat up something like ice, then what's going to happen? Well, it's going to get hotter and eventually it's going to melt, right? That is exactly what we want to try to get a handle on. Does the temperature just keep increasing as you add thermal energy to a substance? Or is there a point at which, even though you're adding more heat, there's no more temperature increase? So you can see, I'm going to draw a graph that I've drawn the axis of here. And I've made it really big, like as big as half the page. And I'm going to label the x-axis with heat energy and the y-axis as temperature. The x-axis could also be thought of as time passing, but I'm going to label the x-axis as heat. Remember, the symbol for heat that we've learned is Q, and that's measured in joules. And the y-axis I'm going to label as temperature. And it doesn't really matter what the units of temperature are here. We'll say degrees Celsius. And we're going to start off with the temperature being really, really low. Maybe even below zero. So don't assume that this is equal to zero. Maybe this could even, like I said, be a Fahrenheit or a Kelvin scale. I'm going to go ahead and put a beginning of a line right here somewhere, really, really low. And I'm going to label that line A. And then I'm going to draw a couple different segments of a line like this. And I don't know if I drew that one perfectly flat, but it's supposed to be level. So forgive me that it's not completely level, but I'm going to label these points as B, C, D, E, and F so we can talk about what's happening at the different stages of the graph. A heating curve like this, if you think about it as being read left to right, it would be a heating curve. If you think about it as reading from right to left, it could be a cooling curve, but it's basically showing where different states of matter exist. So I want to label where solid, liquid, and gas are. See if you can think about where solid, liquid, and gas would be labeled on this graph. It really depends on the temperature. So this part of the line is going to be labeled solid. And this, I'm just going to write the word liquid right over the line there, and I'm going to write gas right here. The other parts of the line that I want to label are going to include phase changes that are occurring. And the key idea here is that if you heat a solid like ice, let's say we're starting at negative 40 Celsius, very, very cold, and you heat it up, eventually you will get to its melting point, also known as its freezing point. And when you do, if you continue to add heat energy, then we're going to have melting occur. But if you were going from right to left, then we would have freezing occur. So I'm going to write melting. If we're going from right to left, and I'm going to write freezing. Because, of course, at the melting point, which is what this temperature right here on the axis corresponds to, is the temperature at which both melting occur or freezing occur. So I think it's important to note that at this temperature on line BC, both liquid and solid can exist. Now I'm going to continue that reasoning and go up here and draw two lines. If I'm on the journey between point D and point E, then I'm going from a liquid to a gas. As I heat energy, that is called vaporization. And if I'm going from a gas to a liquid, that's called condensation. Notice that on line DE, if we are at that temperature, which corresponds to what we'd call the boiling point of the substance, then both gas and liquid can exist. So right at the boiling point, they both exist. The graph has a lot of information in it, but one of the most important ideas is that as I heat up a substance, the temperature does not just continue to increase. Once I get to, for instance, the melting point or the freezing point, the energy that I put in is actually being used to disrupt intermolecular forces and cause the melting process to occur. That will continue to occur until all of the substance has melted. At that point in time, at point C, the sample is 100% liquid, and the liquid will begin to warm if I continue to add heat energy. That will happen until we get to the boiling point. If this is H2O we're talking about, then at 100 degrees, I will start to see a mixture of gas and liquid, right? And I will keep adding energy and keep adding energy as all the liquid vaporizes until no liquid remains. At point E, it is 100% gas, and the temperature of the gas can now increase to 110, 115, 125, and so on. So there's a lot of information in here to unpack. And we may know that there is even some evaporation which may occur at room temperature, and there may be some condensation which occurs at room temperature. So this is a bit of a simplification, but it is an important representation of how temperature and heat are related. And there's a few other points that I want to make underneath this graph. We're going to write a few sentences. The first bullet sentence that I want to write is it's about the slope of the lines A, B, C, D, and E, F. The slopes of those lines are related to the specific heat capacities of the substances that are on this graph. So if this is the heating curve for water, then we're talking about the specific heat capacities of ice, liquid water, and steam. But this could also be for instance, heating curve for something completely different, like acetone or wax. When I say they're related to the specific heat capacities of the solid, liquid, and gas phases, then more specifically, they are the reciprocals. In other words, where the slope is really steep, that means it is a low specific heat capacity. In other words, very little temperature is required to get, very little heat is required to get a big temperature increase. If the slope is very shallow, then that would be a very large heat capacity because it takes a lot of energy to get the temperature to rise by a degree Celsius. Next, I want to write a bullet talking about points B and C. Points B and C are at the melting point, which we'll abbreviate MP. And that is also known as the freezing point. And that is where both solid and liquid exist. So it's important to note that if we're at the freezing point exactly of water, ice can stay ice and water can stay water. Both phases, if you have a glass of ice water and it's at the freezing point of water, are going to exist at equilibrium. Freezing is happening, but melting is happening as well. And so there's no real change. If we're a little bit warmer than that, then melting will occur. If we're a little cooler than that, then freezing will predominate. But exactly at the melting point or the freezing point, if you could manage to keep it at exactly that temperature, then both those phases of matter will continue to exist. And of course, the same can be said for points D and E. We'll make a similar statement. The boiling point, which I labeled on the graph as BP, is also known as the condensation point. And of course, at that temperature, we're going to have both liquid and gas existing. Points D and E are at the boiling point, aka condensation point, where both liquid and gas exist. Now, there is one more concept I want to include here, and that has to do with the length of lines BC and DE. I'm going to label this, you can watch how I'm going to write this carefully. I'm going to write lengths of lines BC and DE, and then I'm going to start a new line, are the heat of fusion and heat of vaporization, or correspond to the heat of fusion, which we're going to label delta H FUS, and heat of vaporization, delta H VAP. And those I want to label on the graph a little bit more carefully. So delta HFUS is the heat of fusion. And this is not fusion as in nuclear fusion. This is fusion as in if you want to weld two metals together, you need to melt them and then they will fuse together. And heat of vaporization. And these terms are referring to the amount of energy that is associated with those phase changes. So the heat of fusion is the amount of thermal energy needed to melt a substance. And the heat of vaporization is the amount of energy needed to vaporize it. And we mean how much energy it takes to vaporize it at its boiling point, or how much energy it takes to melt it at its melting point. The amount of energy that it takes to melt something at its melting point is also the amount of energy that's released when an object freezes at the same temperature. So I'm going to move up to the graph one more time, and I'm going to draw two big boxes. One of them around this entire region here, and one of them around this entire region here. And I want to label these as the heat of fusion and heat of vaporization. Just because and it's even best if we make those lines go all the way up to points D and E, but I'm not going to fuss about it too much here. Too late. However, I want us to know that heat of vaporization is not only going to pertain to the amount of energy it takes to vaporize a substance at its boiling point, but also the amount of energy that is released when it condenses at its boiling point. For instance, if steam condenses on your hand, you know you're going to get burned because a lot of energy is being released from the steam to your hand. The amount of energy that it takes to melt a substance at its melting point is the same amount of energy that will be released when a substance freezes at its freezing point.